Hi everyone, welcome back. In this video, we'll try to see the difference between repartitioning and coalesce in Apache Spark. First, let's try to see how partitioning works in Spark. Whenever Spark reads data from a data source, it tries to store the data in multiple partitions. So as mentioned, as shown in the video, it, this data frame has 6 partitions stored across 3 nodes. Partition 1 and 2 on node 1, 3 and 4 on node 2, 5 and 6 on node 3. So if we would like to increase or decrease the number of partitions, we have uh, different methods. So one of them is repartitioning. So let's try to understand how a repartitioning works. So this is the syntax of repartitioning. Data frame dot repartition, and we have to provide the number of partitions and also columns based on based on which the repartitioning should happen. So for now, let's consider we have performed data frame dot repartition of 3. So from these 6 partitions, we want 3 partitions after performing this repartitioning. So here we can see, right, there is a lot of shuffle happening across the nodes uh, because this repartitioning involves full shuffle. Data from partition 1 will be shuffled from this node 1 to node 2 and node 3, and same for partition 3 and 4, also shuffled from node 1, node 2 and node 3, which means all the partitions are shuffled across the nodes, and shuffle is a costly operation. So let's try to see how a coalesce works. This is a syntax of coalesce. Data frame dot coalesce, and we have to provide the number of partitions. So the same example here, if we can see, right, uh, there is no shuffle happened. That is what Coalesce did here is it merged these two partitions and created a new partition out of it. In this same on node 2, P3 and P4 are merged to create a new P2 partition. P5 and partition 6, it merged and created a new partition. So here you can see, right, there is no shuffle across the partitions. It just merged the partitions that are on the same node so that shuffle operation will not happen. So let's try to see this in live. Yeah. So here, if you can see, right, what we are doing is I have read from a CSV file, mobile logs.csv, and I am just printing the schema, and I am selecting only these columns: signal, network, status, provider, and satellite. And on top of it, I'm performing a group by operation on network, and also performing aggregation of sum of satellites and renaming it as total satellites. And then I'll print 5 rows, and we'll try to run this explain on the data frame. So here, if you can see, this is the schema. This is the schema of that CSV file where we have latitude, longitude, signal, network, operator, status, description, and satellites, all these columns. So this is the final output that we got, and the network and the total number of satellites for that. For Vivo, we have 504. And if we can see here, this is the physical plan what Spark created for this job. So let's try to understand this. So the first stage is file scan. So it read the CSV file, and one observation here is you can see, right, it read only network and satellite. So even this has these many columns, it read only network and satellite because network and satellite are the columns that we are performing operations on. So Spark does this optimization by itself. That is called push down, predicate projection push down, which means even though we have multiple columns, because we want only these 2 columns, it performed that operation optimization that it is not going to read the other columns. So it does by itself. And the next stage is hash aggregation. So it performed a hash aggregation, and one observation here is partial sum. So let's try to understand what is partial sum. in meantime. And here we can see there is a exchange operation happen, and also again hash aggregation. So one more observation is here it performed final sum, and that is how it came to this final execution. So let's try to perform Coalesce here and see how the physical plan looks like. Let's try to coalesce it into one partition. Yeah. Now you can see right in this physical plan, the first stage is file scan read CSV, and then it performed coalesce operation, and then it performed hash aggregation, and here you can see right it is sum. We don't see partial sum and also final merge sum. We directly see the sum, and the main point is that there is no exchange happening here, but that means there is no shuffling of data. So this is how Coalesce tries to eliminate the shuffle whenever it is possible. And also let's try to see the DAG. So this is the DAG when we executed that code without Coalesce. So scan CSV. The next stage is hash aggregation. So here we can see exchange, which means shuffle operation. Also one more hash aggregation and then the final result. Let's try to see the DAG for Coalesce. Here you can see right, it scanned CSV, performed Coalesce, and then hash aggregation. So here you can see right, there is no shuffle involved. And coming back, yeah, so partial sum and final sum. So if we consider the data has two partitions, and these are the rows. So A has two occurrences, B has two, C and D two records in partition one, and same number of records in partition two. So what it did is, so it did a partial sum before even having a shuffle operation. It performed a partial sum, which means in this partition itself, it added these two similar rows, and it created A as two occurrences, B as two, C two, D two. So same operations on P2 as well. So now it performed a shuffle operation, and then the final aggregation is A has four values, B has four, C has four, D has four. So this is how it happened. So let's try to see what it would be without this partial sum. So now if we consider to perform any aggregation, the similar data should be on the same partition. So records records with A should be on partition 1, B also should be on partition 1, and CD should be on partition 2. So let's see how many rows shuffle must happen here. So these two and these two, four rows must shuffle to P1, and C and D should shuffle to P2, which means there are total eight shuffles happening, and then it can perform this aggregation. So now because it has this partial sum stage, let's see how many records are shuffled. So before shuffling itself, it did a partial aggregation. So now C and D has one record, A and B has one. So two records should shuffle from P2 to P1, and these two should shuffle from P1 to P2. So the total number of shuffle is 4. So in the previous case, if it does not has this stage, there should be 8 shuffles happening. So this is how it reduces the number of shuffles happening. Spark does this. So this is the difference between repartitioning and coalesce. So whenever we would want to reduce the number of partitions, we can go with coalesce. And if you would like to increase the number of partitions, we can go with repartition. So we can reduce the number of partitions with repartitioning as well, but there will be a lot of shuffle. Uh, Thanks for watching.